So what we want to look at here is the transpose of a matrix, right? So if I have some matrix A and the matrix has m rows and n columns, right? Then the transpose of A, right, which is denoted by A transpose, right? A with superscript T here, right? Okay, so has m rows and n columns, then A transpose is going to have n rows and n columns, right? So you're going to, the number of rows and the number of columns are going to switch, right? Okay, so that's the first thing in transpose, and then the next thing in transpose is that by definition, the ijth element of A transpose is equal to the jith element of A, right? So a next way to write that is this equation here, which is if I have A transpose and I look at the ijth element of it, then the ijth element, so in other words, if I have A transpose and I look at the element in the ith row and the jth column, right, then that's going to be equal to the element in the jth row and ith column of A, right? Okay, so let's see this definition, right? So here are some examples of matrices, different matrices A, B, and C, A, B, C, and D. And these are the transposes in the second row, right? Alright, so I have this matrix A over here. Notice this matrix is a 3 by 4 matrix, so it has 3 rows and 4 columns, right? And so it's m by n, where m is equal to 3 and n is equal to 4, right? So the number of rows is 3, number of columns is 4, right? And A transpose, the number of rows of A transpose is going to be equal to the number of columns of A, right? So you have, notice you have 4 rows in A transpose, and that's equal to the number of columns in A, right? And similarly, the number of columns that you have in A transpose is 3, and the number of rows that you have in A is 3, right? So the number of rows going from A to the number of rows and columns of A when you go from A to A transpose will switch, right? Okay, so let's look at this. Let's look at an example of this over here, right? So remember what this ij is doing for you, right? This ij is locating an element in row I and column j, right? So let's say if we consider the case when I is equal to 1 and j is equal to 2, right? So what we're looking at is an element in row 1 and column 2, right? Okay, so an element in row 1 and column 2 of A transpose, if I'm looking at this here, right? The element of row 1 and column 2 is A21 over here, right? And you want to notice that this element over here, which is in the first row and second column, so the I is equal to 1 and j is equal to 2, is equal to the element in of A, right, that is in the second row and first column, right? Okay, so this element in A transpose is in the first row, second column, and this element over here is in your second row, first column, right? Okay, so here the I is equal to 1 and the j is equal to 2, right? Here the I is equal to 2 and the j is equal to 1, right? So you see in that the ij, right, this indexes, if you're looking at the element, this element here that is in first row, second column, right? So if I wanna, if I'm looking at A transpose and I look at the element in the first row and second column, right? What this is saying is that that's going to be equal to the element in A that's in the second row and in the first column, right? So that's what is going on here, right? Okay, and it's more intuitive. You could sort of see pretty easily. I mean, I'm sure you've seen this before, what A and A transpose are, right? So to go from A to A transpose, right? Basically what you're doing is you're taking the rows of A, and the rows of A are going to form the columns of A transpose. Notice this first row over here is equal to this first column here, right? Second row is equal to second column. Okay, and third row of A is equal to third column of A transpose, right? Okay, but this over here, this definition here is useful for when you're doing proofs, right? And when you want to prove certain things about certain properties of A transpose, right? And in particular, the ones that we will look at would be these four over here, right? Okay, so if I want to prove, say, A transpose is equal to A, right? What I would need to do is I need to go to the definition of the transpose, right? Okay. Right, and then some more, say, simple examples over here. If this is B over here, right, then to form your B transpose, well, what you're doing is you're gonna, the rows of B are now going to form the columns of B transpose, right? So first row of B, which is 2, 3, is going to be first column of B transpose 2, 3. Second row of B, which is 1, 4, second column of B transpose, and uh, third row of B is third column of B transpose, right? Okay, so some other cases, if C is just this row as matrix with one row and three columns, right? So if you want, this is like a row vector over here. When you take the transpose of it, right, this row will become a column over here, right? So if you want, when you have a row vector and you take the transpose of it, you get a column vector here, right? Okay, and one last thing is if you just have a matrix with a single entry in it, which is 1 by 1, right? Well, there's only one row in this, and this one row has size 1. It has one column in it, right? So this single row, what you do is you form a column over here, right? But this column will just have one entry in it, which is this 4, right? Okay, so if you have a 1 by 1 matrix here and you take the transpose of it, you just get back the same thing, right? And you see in an example here, right? Okay, and then also here, right? So I said over here, one easy way to see how you construct B transpose from B, right, is you're just gonna exchange the rows. Well, the rows are gonna become the columns of B transpose, right? But in the case of when you have a square matrix, right, so a square matrix is the number of rows is equal to number of columns. So this is a 3 by 3 square matrix, right? How you form the transpose, again, you can do to form your transpose, right? What you're gonna do is you're gonna take you can look at it this way, that you take your first row over here, and then that's going to be the first column of A transpose, right? Likewise for the second row, it becomes the second column, right? But a next way to look at this, the formation of A to A transpose when A is a square matrix, is you can in fact use the diagonal of A, right? And by diagonal of A, I mean this dashed line that they have over here, right? And the diagonal of A has these three matrix entries in it, 1, 7, and 6, for this 3 by 3 matrix, right? And how you'd form the transpose in this case, right, is the diagonal will in fact stay the same, right? So you notice the diagonal stays the same in the A transpose. This is your matrix A with diagonal 1, 7, 6. And this is your matrix A transpose with diagonal 1, 7, 6, right? Right, so that stays the same, but when you form the A transpose, how you're going to form your A transpose is to form the A transpose, you reflect across the diagonal, right? Okay, so notice this minus 2 goes into the position where the 3 was, so your minus 2 comes over here, and then the 3 is reflected and comes up on top on this position here, right? So if you want, when you form the transpose, the minus 2 and the 3 are going to exchange positions here, right? And this is a reflection in this in the diagonal 176, right? And likewise, this 4 over here is when you form the transpose will go into the position with the minus 5, and the minus 5 will go into the position with the 4, right? And you have a reflection in the diagonal, right? Okay, so that is what these arrows indicate. And so one way you can, if you have a square matrix, and this really more works for square matrices, right, is that if you want to form the transpose, your diagonal is going to remain the same, right? And then what you do is you reflect the elements across this main diagonal here, right? All right, so our next definition is if I have a square matrix and I take the transpose of A, And when I look at that transpose of A, if that transpose of A is the same as the original matrix A, right, then this matrix A is called a symmetric matrix, right? Right, okay, so let's remember for a square matrix, well, we saw a intuitive way to construct a transpose, right? To construct a transpose of a square matrix, what you do is you reflect in your main diagonal, right? So for example, this -2 will exchange the position with 3, and the 3 will go to position 2, right? Okay, so a matrix, a square matrix, and this is A, and we form the A transpose, right? And you want to notice, well, the definition of symmetric is that A transpose is equal to A, right? So this is a matrix A over here, and this is A transpose, right? But if you look at A and A transpose, right, the diagonal entries are the same, right? Because you have 1 over here, 7 over here, and 6 over here. 1 here, 7 here, and 6 here, right? But the A is not equal to A transpose, right? Because if you look at this position of this element over here, right, in your second row, first column, right, that's not equal to the element in the second row and first column of A, right? Okay, so the A is not equal to A transpose in this case, right? So this matrix A over here, when you take the transpose of it, the A transpose is not equal to A. So if you take A, you don't get this equality over here, right? So this A over here is not a symmetric matrix, right? On the other hand, if I consider this second matrix, right, the one in the middle here, right, and so I take this as my matrix A, right, when I form the transpose by reflecting in the diagonal, and remember this is how you can form the transpose by reflecting in the diagonal stays the same, right? So for A over here, if I reflect in this main diagonal, this 4 will fall. The 4, I have same elements, 4 over here and 4 over here, right? So when I exchange, the 4 goes there and the 4 comes back, right? Okay, so that doesn't change. If I consider the 5, right, the 5 over here is the same as the 5 over here. Likewise, the 0 over here is a 0 over here, right? So if I take the transpose of this matrix here, I will get back the same thing, right? Okay, and notice you have a symmetry. Okay, so this matrix over here, this satisfies your condition that A transpose is equal to A, right? If I take the transpose of this second matrix over here, I will get back the original matrix, right? Right, so this is an example of a symmetric matrix, right? And the next way you can see what a symmetric matrix is, right? Is if you take a look, so this is your main diagonal, right? So in this case, for this matrix, the main diagonal is 1, 7, 6. In this case, the main diagonal is 1 minus 3, 7, right? And in this case, what you have for this matrix is that you have a symmetry about your main diagonal, right? It's 4. If you reflect, right, 4 will reflect to 4, the 5 will reflect to 5, the 0 will reflect to 0. And likewise, on this side, the 4 will go to 4, the 5 will go to 5, and the 0 will go to 0, right? So this has a symmetry about your main diagonal, right? So two ways, if you want, you can see if a matrix is symmetric. You'd have the symmetry of the entries across your main diagonal, or you could actually work out the transpose and check to see that this statement is satisfied, right? That A transpose is equal to A, right? All right. Next definition that we're going to have is skew symmetric now, right? So a matrix is said to be skew symmetric a matrix is skew symmetric if when you take the transpose you don't get back the original matrix, but what you get back is minus of the original matrix, right? So for symmetric, it's A transpose is equal to A. For skew symmetric, the A transpose is equal to minus A, right? Okay, so one way to check for, and this over here is an example of skew symmetric, right? Now, one way to check to see that something is skew symmetric, right, is you look at your main diagonal here, right? And when you consider the symmetrical elements across your main diagonal, here you have 1, and on the opposite position you have the negative of it, right? -1, right? And here I have 2, and here I have the negative of it, -2. Here I have 4, and here I have the negative of it, -4, right? Okay, so that's different from symmetric, right? For symmetric. Okay, so that's different than symmetric, right? Because symmetric, if you're looking at your main diagonal, the for this 4, what's the symmetrical element across the main diagonal is the same, right? Likewise, this 5 over here, what's across your main diagonal is the 5, right? In this case, what's across your main diagonal, the opposite element, if you want, is the negative of it, right? Okay, so that's what you're looking for in skew symmetric, right? You'd have your main diagonal, and then what's reflected in the main diagonal would now be the negative, right? And the next thing with skew symmetric is that your diagonal entries are just going to be equal to 0, right? Okay, so for a skew symmetric, that's what you're looking for, right? The diagonal, the main diagonal over here has to be equal to 0, right? And then uh, when you consider your reflection about your main diagonal, the reflection when you consider, say, like an element is this, the reflection would be across the main diagonal would be negative. Okay. Alright, so let's just recall what we talked about previously, which was row space and column space, right? So we talked about this in a previous lecture, right? So I have a matrix A, right, such as this one over here. The rows of this matrix, there's 2 rows, 1, 2, and 0, 1, right? I regard this row over here as a row vector, such as 1, 2. I regard your second row over here as a row vector, which is 0, 1 here, right? And your row space of A is a set of all linear combinations of these rows here, right? Okay, so and then so you take the span of these 2 rows, and this is your definition of span, right? Which you should know by now, right? So any some scalar times first vector, some scalar times second vector, you add them, and you can take any possible scalar here, C1 and C2 over here, right? So that's what this notation means, right? So this is row space, right? And we saw this already. And we talked about finding a basis for row space, right? So I have this matrix A over here. The row space would be what you would get by taking linear combinations of 1, 2, 3 rows here, right? How you get a basis for your row space is you take A, you apply Gauss-Jordan to A, right? We said that the row space doesn't change when you apply Gauss-Jordan because the A and the result the Gauss-Jordan, which is called V, right? They're row equivalent, and row equivalent matrices have the same row space. Anyway, so to get a basis for your row space of A, what you do is you take your matrix A, you apply Gauss-Jordan until you get an RREF. So your Gauss-Jordan terminates at an RREF. And this RREF over here, the non-zero rows, which would be these 2 non-zero rows, would form a basis for the row space of A, right? Okay, so we did that in a previous lecture, right? And your basis would be your non-zero rows. So this is your first non-zero row, and you write it here as a row vector. Second non-zero row, write it here as a row vector, and this is your basis for your row space of A, right? Okay, and then we also looked at column space, right? So I have a matrix such as A over here, right? And what I'm going to do now is I'm looking at the columns, right? Okay, so this has 2 columns. First column is 1, 0. Second column is 2, 1. And what your column space is, you take an all linear combination of your columns here, and you have 2 columns in this case, right? So you take the span of these 2 columns. And this is your definition of the span of these 2 column vectors here, right? Okay, so, but what I didn't do so far is give you a method to find a basis for column space, right? So that's what I want to talk about now, right? Okay, so, well, how we're going to do it is we're going to use transpose, right? So we're going to take the A, if we want to talk about the column space, right? You're going to take the A, take the transpose of that. So the columns are going to convert to rows, right? And then you use your theory for row space and so. And that's how you're going to get your basis, right? So let's see how it works over here, right? Okay, so first thing I want to talk about is that if I want to get to the column space of A, what if I want to have an idea of what the column space of A is, right? I can do that by looking at the row space of A transpose, right? And I'm saying that the column space of A you can actually identify with the row space of A transpose, right? So what do I mean by that? So this is a matrix A over here, right? This is a 2 by 3 matrix, and this is A transpose, right? Yeah. In this case, the matrix is not square, right? This whole theory would also work if the matrix is square, but this is not square, right? Okay, so this is, I have two rows over here, and I form the transpose, right? Notice here, first row over here becomes the first column, second row becomes the second column, right? So this is A transpose, right? Right, okay, and let's see, well, what's column space of A, right? Which is what I'm interested in, right? Column space of A, what you're doing is you're taking your columns. In this case, you have three columns over here, 1, 4, 2, 5, and 3, 6, right? And you're taking all linear combinations of those, right? So this is your column space of A, right? Right. On the other hand, well, what's the row space of A transpose, right? So this is if this was the A, this is the A transpose over here. And notice, so this here you have three rows, right? 1, 4, 2, 5, and 3, 6, right? And you want to notice that this first row over here has the same entries as your first column over here, right? This column, if you regard it, this is a column vector here. So the 1, 4, you regard the 1, 4 when you're forming a column space as a column vector. So the column vector here is 1, 4 over here, right? And if you're looking at your first row over here and you're forming a row space, the vector that you're using is 1, 4, right? Which is this 1, 4 over here. And the point that I want to make is that your 1, 4, the 1, 4 as a row vector and the 1, 4 as a column vector are basically the same thing, right? It's just written in here is written vertically and here is written horizontally, right? But when you start manipulating it like this over here, you end up getting the same thing, right? Okay, so anyway, so your the columns that you're going to take the span off to form your column space would be 1, 4, 2, 5, and 3, 6, right? I notice when you form the transpose and you take the rows, you get the same, you get corresponding rows, right? So here I get row 1, 4, 2, 5, and 3, 6, right? So this 1, 4 corresponds, this row vector 1, 4 corresponds to this column vector 1, 4. This row vector 2, 5 corresponds to this column vector 2, 5. Row vector 3, 6 corresponds to column vector 3, 6, right? And when you take the span of this, right, what you're going to get is you're going to get a subspace, which is basically the same thing as this one over here. The only difference between the subspaces is here you're writing the vectors in the subspace as rows, and here you're writing them as columns, right? So that's what I mean. You can identify a column space of A with row space of A transpose, right? If you have your column space of A, how you would get the row space of A transpose is you just take your vectors and you just write them as rows, right? And if you have your row space of A transpose and you want to get the column space of A, right, what you do is you could just take these row vectors here and now write them as columns, right? So there's an identification between them, and I'm saying that both of these are basically the same thing, right? There's um, a more precise way to say that they're basically the same thing is that these are isomorphic, right, as vector spaces, right, which means that you can get a map going from column space of A to row space of A that is one-to-one and onto, right, and that preserves the operations, the vector addition and the scalar multiplication, right? So the map in this case to go from to identify column space of A with row space of A transposes, the map is you taking this column over here and you're just converting it into a row vector, right? That's the map, right? But we didn't get into isomorphisms as yet. We'll get to that when we start talking about like linear transformations and probably like in about 3 or 4 weeks or so, right? But for the time being, you want to realize that column space of A is essentially the same thing as row space of A transpose, right? So there's an identification between them, right? Okay. Now that we know that column space of A could be identified with row space of A transpose, what we could use that for is we could use that to get a basis for column space of A, right? So how you're going to do it is if you want to get a basis for column space of A, right, what you do is you find a basis for the row space of A transpose, right? And this would be row vectors, and all you do is you just take those row vectors and you just write them as column vectors, and that would give you a basis for column space of A, right? So let's see how it works, right? I have this matrix A over here, right? And I want to get a basis for the column space of it, right? Okay, so first thing you're going to do is you form A transpose, right? So A transpose is, well, the exchange rows for the columns, so this is A transpose over here, right? And now what I want is a basis for row space of A transpose, right? But how do you get a basis for row space, right? We know how to do that, right? What you do is you apply Gauss Jordan to this matrix here, the A transpose, right? And when you apply Gauss Jordan to this matrix here, right, with 3 rows and 2 columns, what you're going to get is this would be your RREF that you get from the Gauss Jordan, right? Okay, and then the non-zero rows of this RREF over here, right, which is the 1, 0, and the 0, 1, right? That would form a basis for the row space of A transpose, right? So all of this part over here, we know how to do already, right? We saw examples of that already, right? You just have a matrix that happened to be called A transpose, and to get a basis for the row space of it, you apply Gauss Jordan, and you take the non-zero rows of the result, right? Result in RREF, right? And that's going to form a basis for the row space of this guy, right? And the basis of the row space of this guy, right? The row space of A transpose, right? So this is my row space of A transpose, right? Written down. So this 1, 0, and 0, 1 would be a basis for this row space here, right? Okay, but this row space over here is the same thing is identified with this column space, right? Right? And this is the column space that I'm interested in, right? Notice this is the row space of A transpose. Um, the vectors here 1, 4, 2, 5, and 3, 6, and I have the same vectors over here. It's just that they're written in columns over here, and they're written in rows over here, right? Okay, and what that means is because this one is essentially the same thing as this one, is just a matter of how you write it, okay? And I know that this 1, 0, and 0, 1 is a basis for uh, this row space over here. Then in order to get a basis for the column space, right, all I need to do is just rewrite this 1, 0, and 0, 1, these row vectors as column vectors, right? And these column vectors are now going to form a basis for this column space, right? Okay, so it's really, if you understand that this here is a basis for this row space, right? All you're doing is you're just rewriting everything, right? You're writing all your row vectors as column vectors, and when you do that, right, what you have here is column space of A, and therefore these two would be basis for your column space, right? So one more time, if I want to get a basis for column space of a matrix, right, what you do is you form the transpose of the matrix, apply Gauss Jordan, get the non-zero rows here, right? And then what you do is you just convert these non-zero row vectors into column vectors, and these column vectors would be a basis for your column space of your original matrix. Alright, so let's look at Theorem 3.13 now, right? Okay, so what this is saying is, well, it's giving you relationships among the various dimensions of your fundamental subspaces, right? anyway, so I have a matrix A over here, right? And for matrix A, we saw how to get the null space of your matrix, right? And in fact, we saw how to get a basis for the null space of your matrix A, right? We saw how to get a basis for row space of A, right? And we just saw how to get a basis for column space of A, right? So because I know how to get a basis for each of these, right? It means I know how to get the dimensions of them, right? And in some cases, I have a more direct formula for getting the dimensions. But what these two are doing for you is telling you that these values, right? So dimension of null space and dimension of column space, right? They're actually related to each other, right? So there's an equation relating dimension of null space to the dimension of column space, right? That is the dimension of null space of A plus dimension of the column space is equal to the number of columns of A, right? And then we have this second one over here, which is saying that the dimension of the row space is equal to the dimension of the column space, right? So you want to remember that we call dimension of row space, we call that rank, right? And we call dimension of column space, we call that column rank, right? Okay, so what this is saying is that if you that rank, which is dimension of row space, is actually equal to the dimension of column space, which is column rank, right? So in other words, uh, rank is equal to column rank, right? So when you talk about dimension of column space, the term column rank is sort of like an artificial construct because it's just equal to rank, right? So people don't really say column rank, right? Because if you calculate dimension of column space, even though you define that as column rank, it turns out that it is in fact just equal to dimension of row space, which is rank, right? So in that sense, you don't talk about column rank, you just talk about rank of a matrix, right? Okay, so let's the proof of this is, in order to prove this, at least my proof of it is done later in the notes, right? There's possibly other ways to prove this, right? But anyway, so if you're interested in seeing what the proof of it is, this is on page 89, but and we will get to that eventually, but you see that requires a certain amount of theory from linear transformations, right? At least this proof here, right? Okay, so for the time being, what I'm going to do is I'm going to show you an example of uh, a matrix and calculate the null space, the column space, and the row space, and show you that the dimensions satisfy these two equations here, right? Okay, so the example that I'm using is from one of the past papers. It's for this matrix over here, right? And I believe we already calculated the column space of this matrix, right? We calculated a basis for the column space of this matrix. No, I didn't. Right? Okay, what I calculated the basis for was this matrix here, right? 1, 2, 3, 4, 5, 6, right? Okay, so this is a different matrix. Anyway, so I have this matrix over here, and I want to get, it's asking me for the bases of all four fundamental subspaces, right? So the four fundamental subspaces are null space, column space, row space, and what I'll get to later in the lecture is left null space, right? Okay, but for the time being, we're looking at three of those four fundamental subspaces, which would be null space, column space, and row space, right? Alright, so I have, this is my matrix, and let's see, and as I said, this is a past paper, so this is 2014, and the solution is also on the website. Alright, so this is the matrix A over here. I just happen to call it C, right? But it doesn't make a difference what I call it, right? Okay, so this here is my matrix, and in order to get a basis for the row space, what you do is you apply Gauss-Jordan to this matrix, and when you apply Gauss-Jordan to this matrix over here, you'd get this RREF, right? And a basis for the row space would be the non-zero rows of this RREF, and a basis, the non-zeros are 1, 0, 0, and 0, 1, 0, right? So these are a basis for the row space, right? If you want to get a basis for your the null space, right? What you do is you're gonna form the system associated to this, right? Uh, Form a system associated to this and construct the. Let me show an example of this. So form the system associated to this, and then what you do is then you get the augmented matrix for that system, right? Now, when you form the matrix associated to this, and you get the augmented matrix for that, right? What you get in is you're really just getting back the same matrix, right? The only difference is that you're gonna have constants 0 here and 0 here, right? Which you don't really need to see, right? Because this is a homogeneous system, right? Anyway, so we saw an example of calculating null space in the previous lecture, so you could take a look at it and review. It's the same work in here, right? Alright, so really what you're going to be doing to get your null space is you take this matrix over here, form your system, then form your augmented matrix, apply row reduction to that augmented matrix, and what you would get is you'd get this matrix here, right? So really you could just use your working that you had for row space, and you take this over here and you apply Gauss-Jordan to it, right? And then what you'd need is the equivalent system here, right? Because what you need is this here would be associated to the system, and the system over here, the solutions of this system would give you your solution space, right? And that solution space is the null space, right? Okay, so your solution set for this system over here, right? If you read in this, notice here what you have is three variables, x1, x2, and x3, right? So you have two pivot variables here, one over here for x1, one over here for x2, and the x3 over here is free, right? Right, so what that means is that the x3 is free, and I can solve this for the free variables, and when I do that, notice I don't have the free variables showing up over here, right? But that's not really a problem, right? So I have x1 is equal to 0, x2 is equal to 0, and x3 is in fact free, right? So the solutions would be 0, 0, x3, which I can write as x3. I can pull, okay, solutions would be 0, 0, x3, and I can pull out the x3 over there. And therefore, this would be a solution set, right? So this is your null space over here for your system here, right? This is in fact bad notation, right? Because a null space is a solution set for a matrix equation, right? So really, this should be a column vector here, right? So as it is over here, this is correct notation. What I should write this over here as a column vector, right? So the basis for the null space would be 0, 0, 1, right? Column vectors, right? Okay, so that's we see what the row space is, we see what the null space is, and the basis for the null space would be column vector 0, 0, 1, right? And to get a basis for your column space, right? What you do is you take this matrix, and this is what we saw probably like about 5 minutes ago. You take your matrix, this matrix over here, to get a basis for the column space. Take the matrix, form the transpose, which is this is your transpose over here. Apply Gauss-Jordan to the transpose, right? And what you'd have is these two non-zero rows would be a basis for the row space of the transpose, right? And then the row space of the basis for the row space of the transpose, right? To get a basis for the column space, you're going to take these row vectors here, right? Going to take these row vectors and convert them into column vectors, right? This is what I was saying, that you have an identification between columns space of A and row space of A transpose, right? So that is the statement over here, right? So what I'm doing is I'm using the same idea that I had in this example, right? Okay, so the basis here for row space of A transpose would be the 1, 0, and the 0, 1, right? And then what I would need to do is I would need to write that. Matter of fact, it's the same. It just turns out it's the same row vectors over here, 1, 0, and 0, 1. And to get the basis for the column space, right, I need to write this 1, 0 and the 0, 1 as column vectors, right? So the basis for the column space would be the 1, 0 and the 0, 1 here, right? Okay, so now I know well, the bases for all of my three subspaces that I want to consider, right? Um, the ones that I want to consider in, for theorem 3.13, the ones that I want to consider would be null space, row space, and column space, right? Okay, and I now have a basis for null space of A, I have a basis for column space of A, and I have a basis for row space of A, right? And because I have a basis for all of these, right, I know what the dimension is, right? Because the dimension is just a count of the number of elements, number of basis vectors, right? Okay, so first let's check to see that this first equality over here holds for this example, right? Okay, so I want to check to see that dimension of null space plus dimension of the column space is equal to the number of columns, right? Okay, so that is the statement here, right? Dimension of null space with dimension of column space is equal to the number of columns, right? And is that true in this example, right? The example that I just did. Okay, so what's the dimension of the null space? Well, the basis for the null space is 1, 0, 0, right? Remember, there should be a column vector, but still, the amount of elements in the basis is 1, right? So the dimension of the null space is 1, right? You only have one vector in your null space, in the basis for the null space. The dimension of your column space, okay, so the basis for the column space is these two vectors over here, right? The 1, 0 and the 0, 1, right? Okay, so the dimension of the column space is 2, right? So dimension of the null space is 1, dimension of the column space is 2, right? And I have 1 plus 2, and that's supposed to be equal to the number of columns in the matrix, right? And the number of columns in my example matrix here is 3, right? Okay, so you see that your first part of theorem 3.13 is satisfied, right, for this matrix over here, right? Because the dimension of the null space of this matrix is 1. The dimension of the column space is 2, right? And the number of columns is 3, right? So you get that the 1 plus 2 is equal to 3, right? So this matrix A, it satisfies this statement here, right? That is not a proof, right? That is a verification, right, for this particular example, right? Okay, and now we have this second equality, and let's see if that second equality holds in for this example, right? Right. Okay, so the basis for the column space would be these two vectors over here. So the dimension of column space is 2, right? The number of vectors in your basis. And your row space, the row space, the basis for the row space would be these two vectors over here, right? So the dimension of the row space is also 2, right? So one more time, dimension of row space is 2 because I have two basis vectors for my row space. And dimension of column space is 2 because I have two vectors in this basis here for the column space, right? So dimension of row space is 2, dimension of column space is 2, so both of those are equal, right? And that, right, so in this example, the dimension of the row space is 2, the dimension of the column space is 2, and that satisfies your second part of theorem 3.13. Let's go back to the transpose of a matrix because I want to prove a couple of these statements here, right? Okay, so recall how you get in the transpose of a matrix, right? If you have a matrix that is m by n, right, then the transpose, the size of the matrix is now going to be n by m, right? So the number of rows in the original matrix is m, right? Then the number of columns in the transpose matrix is m, right? And if the number of columns in the original matrix is n, now the number of rows in the transpose matrix is n, right? And the definition of transpose is that the ijth element of the transpose, right, is equal to the jith element of the original matrix, right? Okay, right. So let's look at this result over here, right? I have A and B, and A and B are matrices, and you wanna these matrices are of a size so that the expressions are well defined, right? So what do I mean by that, right? So I can't add over here a 2 by 2 matrix to a 3 by 3 matrix, right? In order to do addition of matrices over here, the matrices would have to be of the same size, number of rows and number of columns, right? Okay, and if I consider a product over here of matrices, right? Then the number of columns, if I'm considering just this product, say AB, right? Inside the bracket, right? Then the number of columns of A needs to be equal to the number of rows of B, right? And I have it written over here, right? So A, I'm calling the order of A P by M, right? So M is the number of columns of A, right? And B is the number of rows of M, right? So this matrix multiplication is defined, right? Because in order for AB to be defined, the number of columns needs to be equal to the number of rows, right? Okay, so let's look at this first one over here, right? That what this says is that if I have a matrix A and I take the transpose of it, and I take the transpose of it again, right? A second time, I get back to original matrix, right? And well, that really shouldn't be extremely surprising. So well, you have a matrix A over here. You take the transpose, which means that when you take the transpose, the rows now become columns, right? Okay, so first row over here, 1, 2, 3 became column 1, 2, 3. Second row over here of A, 4, 5, 6 became second column here, right? And when you take the transpose of the transpose, right? So if you take the transpose again, then the columns go back to rows, right? Okay, so your first column now becomes the first row. Second column now becomes your second row. So in other words, you went back to what you had in the beginning, right? So you get back to original matrix, right? Okay, that's an intuitive way to see what's going on via an example, right? But how would you prove something like that, right? Okay, so this class we're not really focusing on proofs, right? But this sort of like simple thing over here, right? I would expect you to know this here, right? Because at least you should have an idea how to do some basic proofs, right? Right, so how are you going to prove this one here, right? I mean, somehow you'd need to write this down and express it correctly, right? I mean, you could say that well, when you form the transpose, the rows exchange for columns, and then when you form the transpose again, right, then the columns exchange back to rows, right? But obviously that is not very precise, right? Okay, so when you're proving things, you want to do it in some sort of systematic way, right? Now, what you have over here is you have this matrix on the left-hand side, and you have this matrix on the right-hand side, right? And if you want to prove that two matrices are equal, right, first thing you need to establish is that the matrices have the same size, right? So, for example, this B and C over here, right? I mean, before you even bother to check the elements, you realize that this is a 2 by 2 and this is a 3 by 3, right? So there's no way that this matrix is going to be equal to this matrix over here, right? So first thing you want to check when you check in for matrix equality is that the matrices have the same size, and by size I mean number of rows and columns, right? So I need to check that the number of rows and columns over here is equal to the number of rows and columns over here, right? So that's the first thing you need to check, right? And the second thing to check in matrix equality is that corresponding elements are going to be the same, right? One thing that you want to check for matrix equality is that okay, so for example, if you consider matrices here A and B, right? These matrices, they have the same size, right? It's 3 by 4, right? You have 3 rows and 4 columns, 3 rows and 4 columns, right? But if once you start looking at the entries, this entry over here is not equal to this entry over here, right? So that tells you right away that the matrices are not going to be the same, right? Because in order for two matrices to be the same, each entry, this entry over here, needs to be equal to that entry there, right? Okay, so alright, so to summarize, if I need to show that two matrices equal to each other, your first approach would be if you want to show that matrix A is equal to matrix B, right? Then the first thing you need to do is they show that the same order, right? Which means that the same size, right? And then you want to show that the corresponding elements are equal, right? So the one in, if it's in a, you have one in a certain position, which is, you could denote as ijth position, then the corresponding, that's going to be equal to the corresponding element in the same position, right? And you want to show that for each possible position, right? So how you're doing that is you just pick any position, right? Any position, and you show for that for any position, and that's how you denote it, the ijth position. Show that for any position that the ijth element of A is going to be equal to the corresponding element in the same position, right, in B, right? Okay, right, so let's see. You want to use that to show that A transpose is equal to A, right? And right, so this is an example that A transpose is equal to A, right? So this is A. This is when I take the transpose, right? And when I take the transpose of it, I get back the same matrix, right? But I want to prove it formally, right? Okay, so the order of the matrix A, you call it something, right? It's m by n, right? So this is a standard way to denote the order of a matrix. M is the number of rows, n is the number of columns, right? Now, when you form the transpose, right? Remember the transpose, the size of the matrix is now n by m, right? That's the definition of transpose, right? Okay, and then when you take the transpose again, right? Well, what's going to be the number of rows in this, right? Well, the number of rows is going to be equal to the number of columns in A transpose, right? So the number of rows in A transpose is M, right? And the number of columns in A transpose is equal to the number of rows in A transpose, right? So the number of columns in A transpose is N, right? So what that shows is that the order of A transpose is in fact the order of same as the order of A, right? So what you establish is that A and A transpose have the same size, the same order, right? So that's the first thing in showing that this matrix over here is equal to this matrix, that the A transpose is equal to A, right? Okay, and now what you want to do is you want to show that corresponding elements are equal, right? Kind of concrete sense that if you want to show that if you establish that the matrices are the same size, so for example these two matrices here, right? If you want to show that they of the first thing you want to show that they're equal, first thing you show is that you show that they're of the same size, but then you need to show that each entry in your first matrix is equal to the corresponding entry in your second matrix, which is not true in this case, right? And how you do it here, right, is you pick ijth element. So you take the element in any position in A, right? So that is what this is saying right here, right? So you're picking some element in A, and this ijth means that it's just the ij could be anything, right? So you're picking an arbitrary element of the matrix A, right? But you're keeping track of it, right? So it's the ijth element, right? Okay, and well, the ijth element of A is the jith element of A transpose, right? And that comes from your definition of transpose of a matrix, right? Okay, and we saw that already, right? So, for example, here that right, the ijth element here, if I consider this one here, which is the 1 3 element, that is equal to the 3 1 element of A transpose, right? So ij over here, where the I is equal to 1 and j is equal to 3, is equal to the ji, right, which is 3 1, right? So third row, first column, right? Okay, so that's a definition of transpose. So first thing we start with this side, right? Pick the ijth element over here, right? And the ijth element of A is equal to the jith element of A transpose by definition of transpose, right? And the jith element of A transpose is equal to the ijth element of A transpose, right? So notice over here, what you're doing is you're going from this matrix here, A transpose, to the transpose of it, right? So if you have a jith element of A transpose, right, that's not going to be equal to the jith element of A transpose. That's actually going to be equal to the ijth element of A transpose, right? Because that's a definition of transpose, right? You have it's just a definition of transpose, right? Right? When you go from a matrix to the transpose, the jith element is equal to the ijth element, right? Anyway, so here I go from ijth to jith back to ijth, right? And notice what with these equalities over here, what I get is any element of A once it's in the ijth position, right? It's going to be equal to the corresponding element of A transpose, right? Okay, and that is in fact, that will show me the equality, right? So this would be how you would prove it, right? First you show that the orders are the same, right? And then you show that ijth element of one side is equal to the ijth element of the next side, right? What I want to do now is I want to prove this fourth one over here, right? That AB transpose is equal to B transpose A transpose, right? All right, so this what inside this bracket over here you have matrix multiplication, right? So let me just remind you about the matrix multiplication and some notation involving this matrix multiplication. I have a matrix A and a matrix B, right? Notice they're not necessarily of the same size, but the number of columns over here is equal to the number of rows over here, right? So the matrix multiplication will be well defined, right? Okay, so how do you do the matrix multiplication? Well, you take your first, you know how to do it. You take your first row over here and then you multiply it against your first column, right? Now notice when you're doing that, when you take your first row over here and you multiply against your first column, right? What you're getting is you're getting a certain entry of your matrix AB, right? You're getting what's in the 1 1 position, right? Okay, so you're getting what's for the AB over here, you're getting the entry that's in the first row and first column, right? Okay, so if in my product over here I want to get for example the entry that's in my say my first row and second column, right? What I would need to do is to get the entry in for AB, right, which is first row second column of AB, right? What you're going to do is you're going to take your first column of A and multiply against your second column of B, right? Okay, so taking your first column of A and multiplying against your second column of B, you'd have A11 times B12, A12 times B22, and A13 times B32, right? Okay, and you see in it over here, right? This is what you get. So when you multiply, use your first row from A against the second column of B, right? Now, one thing you want to notice in this notation, right? What you're doing is you're multiplying A's by B's, right? This one over here, right? this in A11 is indicating that it's from your first row, right? This one over here is indicating that it's also from your first row. And this one over here is indicating that this A is from the first row, right? Okay, this 2 over here is indicating that this B over here is from your second column, right? This 2 indicates that you're from your second column. And the 2 on the end here is indicating it's from the second column, right? So the outside indices over here, when you have this AB, right? This first one here is indicating the row position, right? So it's indicating what row of A you're using. And this second term over here is indicating what column of B you're using, right? And you see what you're doing is you taking first one against first one over here, second one against second one, right? So what you're doing is you're forming a sum, right? And when you multiply and then you add up all of these, right? Notice there's a pattern over here. This one over here will match with this one over here, right? This 2 over here will match with this 2 over here, right? Why it matches is because you're taking first position here against first position here, right? And then this 2 over here matches with this 2 over here, right? This 2 in the second position of the A matches with the 2 of the first position of the B, because you're taking the one in the second, you're taking the second element of the first row and you're multiplying against the second element of the first column, right? Okay, so the point is that when you multiply your row against the column, right? First, and for example, here this is multiplying row 1 against the third column, right? The first entry in the A's is telling you what row it's coming from, and then the third the second position in the B's, right, is telling you what column it's coming from, right? Okay, so when you form this product, you can actually tell that this is corresponding, this is in the AB, right? So remember, when you take your first row and multiply against the third column, right? So when you take your first row and you multiply against the third column, what you're going to get is you're going to get in the AB. Okay, so when you multiply your first row against the third column, right? What you're going to get is you're going to get in the AB, you're going to get the 1, 3 entry, right? You're going to get the entry that's in the first row and third column, right? Okay, so that's just a little review of the matrix multiplication. Now the point is this here, right? I can write in, because I'm always have. Okay, so let's use this same first row and third column, right? Okay, so if I'm using first row and third column, right, the fact that I always have this one is the first element in the A and the 3 as the second element in the B, right, which is indicating that it's going to be the 1, 3 element in the product, right? Then I can actually write this, right? I notice also that it's 1 against 1 over here, it's 2 against 2 on the inside, and 3 against 3 on the inside, right? So this over here I can write in summation notation, right? And that is what I'm saying over here, right? So I have a product, matrix product AB, right? Okay, and this is the jth row of A, and this is the lth column of B, right? Hopefully you can see it, right? So this is an L over here, this is not a 1, right? Okay, so I have the jth row of A and I have the lth row of B, right? Okay, and when I multiply the jth row of A against the lth row of B, right, what I get is the jth element of AB, right? So I get the element of AB that's in the jth row and in the lth column, right? So I get a specific element of AB, right? And I can multiply it out, so AJ1 times B1L, right? And then AJ2 against B2L and so on, right? And notice this over here I can write in summation notation, right? So this product over here, when I multiply the row against the column, I can write this way, right? AJIBIL, where the index here is for the inside over here, right? So it starts with 1, goes to 2, right? And so there's a typo there. This should be 2L there, right? And then you would have 3 here and 3 here and 4 here and 4 here, right? So this here I can write when I multiply the row against the column, right? I can write the result in this using sigma notation here, right? And the idea is that this from this sigma notation, the j is telling me that this element over here is going to be in the jth row and in the lth column of the product, right? Okay. Right, so now let's work on proving this AB transpose is equal to B transpose A transpose, right? Right, okay, so what I need to do is, first thing is I want to show that the order of this matrix AB transpose is the same as the order of the B transpose A transpose, right? And in order to do that, what I need to do is, for the A, I just call the order P times M, right? So I'm just doing this in a consistent fashion, right? So the order of A is P times N. And in order for this matrix multiplication to work, order of B has to be M times N, right? So that's A and B, right? I just need to give it some names, right? So it's like doing a word problem. You need to, if you have oranges and apples, you say X is equal to the amount of oranges and Y is the amount of apples, right? So you need to give it a name in order to work with it, right? So that's what I do over here. Right, and then if A is P by M and B is M by N, right, then the product AB is P by N, right? And so AB is P by N, which means that the transpose is going to be N by P, right? So AB transpose is of order N by P, right? And similarly, well, B transpose would be N by M and A transpose would be M by P, right? So if I multiply B transpose by A transpose, right, I'd have N by M by M by P, so I'd end up with a N by P, right? So both of these have the same order, right? So you just check that way, right? Right, okay, and now what you want to do is you want to show that the any element over here is equal to the corresponding element of across here, right? So I mean over here I use ij, right, the ijth element, but you see I'm going to use index I over here, right? And because I'm going to use index I don't want to use it. I don't want to use it across here when I'm locating the element in the product, right? Okay, so I call this JL, right? JLth element, right? And this, the notes has a typo in it, right? Because this should be M over here. This should not be N, right? Anyway, so this is your correct proof over here on this side. Right, so what I want to get is I want to get the JLth element of B transpose A transpose, right? Okay, so how do I get the JLth element of B transpose A transpose, right? What I'm going to do is I'm going to take the jth row of B and multiply it against the ith row of the jth row of B transpose and multiply it against the lth column of A transpose, right? So that is using the matrix multiplication to get a specific element of your product B transpose A transpose. You take jth row of B transpose and you multiply it against the lth row of A transpose, right? And when you're doing that, how you do that is you do it by multiplying the appropriate elements, right? Okay, so what you're doing is you're going to be running along, and just using this as an example, so you're going to be running along your row over here and then running along your column over here, right? So you're going to have first element of the row against first element of the column, right? Second element of the row against second element of the column, right? So that is what this is saying over here, right? in order to do the matrix multiplication of the jth row, in order to compute the jth row against the lth column, you're doing it entry by entry, right? Okay, so first element of the jth row against the first element of the lth column, right? Then second element of the jth row against the second element of the lth column, right? All right. Okay, so now that you established this is really just using the matrix multiplication. I just need to identify what the ith element of the jth row of B transpose is, right? Okay, so the ith element of the jth row, right, is the jth element of B transpose, right? Because it's jth row and then the ith column, right? Okay, so it's the jith element. This here is the jith element of B transpose, right? But the jith element of B transpose is the ijth element of B, right? So that is Bij, right? Notice there's no transpose or anything here. So one more time, jith element of B transpose is ijth element of B, right? All right, and then over here, right, the ith element of the lth column of B, right? Well, what is that, right? That is, you're looking at the lth column, but it's in the ith row. So this is lth element of A transpose, right? And the lth element of A transpose is the lith element of A, right? So that's where this comes from. Right, so I have this now, right? I have this sum over here, right? And now what I can do is I can rewrite this, right? I just bring the A, I just change the order, right? So this is ALI by BIJ, right? Now, what is this sort of product over here, right? This sort of product over here, what you're doing is, and remember I said this, right? Once you have something like this L is indicating the row it's coming from, and the J is indicating the column it's coming from, right? So this over here, what you're doing is you're taking the lth row of A and you're multiplying it against the jth column of B, right? Okay, and once you're doing that, that gives you the ljth element of this product over here, right? AB, right? Because you're taking the lth row of A against the jth column of B, right? So you get the ljth element of AB, right? And the ljth element of AB is, using the definition of transpose, is the jlth element of AB transpose, right? Okay, so when you thread through this work in here, this statement, right, what you got is you got that if you take a certain element in a certain position of in the B transpose A transpose, so you take the jlth element of B transpose A transpose, it's equal to the corresponding element, the jlth element of AB transpose, right? So that shows that the corresponding elements equal, right? So we established that they have the same size, right? B transpose and A transpose. This over here, B transpose A transpose, has the same order as or size as AB transpose, and then we showed that element over here is equal to the corresponding element over here, and that shows the equality of the matrices. Alright, so what I want to consider now is left null space of a matrix, right? So what left null space of a matrix A is just simply you have matrix A, you take the transpose of it, A transpose, and then you take the null space of that, right? So let me remind you how you get null space of a matrix, right? We did that in a previous lecture. And so I had this matrix B, I looked at this as an example. So this is a 2 by 4 matrix, and to get the null space of B, right, how you get the null space of a matrix is you consider matrix equation Bx is equal to 0, right, where x is a vector of unknowns, right? And this over here, you can Bx is equal to 0, you can do the matrix vector multiplication, right? And when you do that, right, what this matrix equation would be equivalent to this homogeneous system, right? And your null space is simply the solution set of this homogeneous system over here, right? So that is null space of a matrix, right? Null space of a matrix B set up this matrix equation, bx is equal to 0, multiply it out and get your system of equations, and then the solution set of the system of equations is a null space of B, right? Okay, so in this case, what I have is I have a matrix A, and left null space is a null space of A transpose, right? Okay, so let's see an example of that, right? This is my matrix A over here that I'm going to use as an example, right? I want to get left null space of it, right? So I'm going to take the transpose of it, right? And the transpose of it is 1, 2, 0, minus 1, 0, 0, right? That's the transpose. And what I'm considering now is I want to get left null space of this. So I want to get null space of the A transpose, right? So given A, to get left null space, what you do is take the A, you form the transpose, and now with that transpose, you consider a matrix equation of the form transpose vector of indeterminates equal to 0, right? So it's just a matrix with a vector of indeterminates equal to the 0 matrix, and that's just the same as what we were doing to get null space, right? So matrix vector of unknowns and then 0 vector, right? And the left null space is going to be the solution space of the system, right? So take a matrix A, take the transpose of it, and then take the null space of that, right? Okay, so over here to get the null space of this, right? What the null space would be the solution set of this system, so you need to multiply it out. You get, when you multiply this out, you'd have y1 uh, plus 2y2 is equal to 0, which is your first equation. Then you get your second equation and third equation. So you'd have a system over here, and in order to solve your system, you form an augmented matrix, right? Notice over here that the augmented matrix, this matrix here, is just a copy of what I have, right? So this entire step over here forming the associated linear system is somewhat redundant, right? Because really you could just take this and put it over here, right? And you don't even need this vector zeros here, right? Anyway, so once you have this, what you do is you apply a Gauss-Jordan, right? This is a standard way of solving a system of equations. And here what you'd get is this is your RREF, right? And this RREF has an associated system, which is the y1 is equal to 0, the y2 is equal to 0, and this equation that doesn't tell me anything, 0 is equal to 0. So what I get is the solution of this system over here is that the y1 must be 0 and the y2 must be 0, right? Okay, so this system has a unique 0 solution, right? So you're given your matrix A, you take the transpose of it, which is this here, right? And then you find the null space of that transpose, right? And the null space of this transpose over here turned out to be y1 is equal to 0 and y2 is equal to 0, right? Right. Okay, so 0 over here and 0 over here. So solution set, right, is 0, 0. So your null space of the A transpose is just this 0, 0 over here, right? So this is an example of calculating null space of a left null space of A, right? And left null space of A is null space of A transpose by definition, right? Okay, so one more time. If I have a matrix A, to get the left null space, I want null space of A transpose, and that's just what I did, right? And the null space of A transpose is, just, in this case, just consists of the 0 vector alone, right? So it's a trivial subspace of R2. See if I can explain why this is called left null space, right? So, well, how are you supposed to calculate left null space? As I just did, right? If you have A, what you're going to do is you're going to take the transpose of A, form A transpose, and then just set up this matrix equation, right? And the solution set of this matrix equation would be your left null space, right? Okay, so I mean, while I have this in with your set notation and so on, what's really important here is what's on the right hand side over here, right? Anyway, so my left null space is solution set of this matrix equation here, right? So this is your A and this is A transpose, and I have a vector of variables, which is the y1, y2 here, right? And this is equal to the 0 vector, right? Okay, so notice here this is a vector equation, right? And this is a matrix times a vector, and this is a vector over here, right? Now this vector over here you could just regard as a 2 by 1 matrix here, right? So you could really look at this as you have a product of matrices on this left hand side, and you have a product of matrices on this so you have a product of matrices on this left hand side, and you have a matrix on this right hand side, right? Right. Okay, so once you have that, right, what you can do is you can take the transpose of both sides, right? So if you have an equality over here, taking the transpose of both sides does not break the equality, right? Because they're the same thing, right? Okay, so take the transpose of this side and take the transpose of this side, right? And when you take the transpose of this product over here, what you're using is the fact that AB transpose, right? So using this AB transpose is B transpose A transpose, right? Okay, so what would happen is that the order would reverse over here, and then you would have the transpose this, you would have the transpose of this, right? Now this was A, right? And this is A transpose because that's what we need to find left null space. But when I took transpose of this equation, right, this A transpose became A over here, right? And this Y over here became Y transpose, right? Now what you want to do is now you want to look at this equation here, right? Okay, so you want to look at this equation in which you have a matrix. You have a matrix over here, and remember when you're dealing with normal null space, right? When you're dealing with normal null space and you want to get a null space of a matrix B, what you're doing is you're considering a matrix equation of the form Bx is equal to 0, right? But in this case, what we want is left null space, right? So what you're actually doing is you when you form your transpose of this equation, you see in that your vector of variables here is now on the left hand side, right? It's not on the right hand side over here. So it's of this form, matrix A over here, right? And then you have a vector of variables on the side, right? Okay, so what you're trying to do is you're trying to find solutions. So you're trying to find a solution vector over here such that when you multiply on the left hand side now, right? And again, one more time, if you're doing normal null space, right? What you're doing is you're trying to get solutions when you multiply. You have a vector here on your right hand side, right, of the matrix. In this case, what you're looking for is you're looking for vectors on the left hand side, so that if you find a solution, this solution times your original, and this is the original matrix A over here, you get the 0 vector, right? So that's an idea of why you call it left null space, right? You're trying to find vectors such that when you multiply on the left hand side, okay, so left null space of your matrix A, you're trying to find vectors on your left hand side such that when you take a vector and you multiply it by A, and this vector is on your left hand side, you get the 0 vector, right? Alright, but all of that is equivalent to just finding null space in a normal sense of A transpose, right? So this is really for me to explain to you where that word left comes from, right? But for the purposes of your calculation, and so if you want to find left null space, what you do is you take your A, take the transpose of it, and then you form your null space in the normal sense, right? Okay, as what I did in this example. Right, so now let's take a look at a formula for dimension of your left null space, right, in terms of rank of A, right? Okay, so what this is saying here is that if I have a matrix A and I get the left null space, then the left null space, the dimension of it is M, which is the number of rows of my original matrix, minus the rank of A, right? Okay, so if for some reason you already know what the rank of A is, and that's really not that hard to find, right? Because if you have A, you could apply Gauss-Jordan and count the number of non-zero rows of the RREF that you get, right? Okay, so rank is relatively easy to calculate, right? So what this formula over here is giving you probably a fast way to determine dimension of left null space, right? Because sometimes you may just want the dimension of it, right? You may not actually want the basis and so, right? You may not exactly want to see like the solutions, right? You just want the dimension. Okay, right. So according to this here, the dimension of the left null space of a matrix, a m by n matrix, is m minus the rank of A, right? Notice this is rank of your original matrix. So let's see if I can explain this here, right? So what do I need to use, right? What I need to use is I need to use this statement here, right? So this first one, right? Okay, so right, so here if I have a matrix A, right, then dimension of null space of A plus dimension of column space of A is equal to the number of columns of A, right? We talked about this, right? So that's what I want to use for A transpose, right? So that's how I'm going to start off. So this works for any matrix A, right? So in particular, it'll work for A transpose, right? Okay, so dimension of null space of A transpose plus the dimension of the column space of A transpose is equal to the number of columns of A transpose, right? But remember what my setup is here, right? A is m by n, right? So if A is m by n, then if A is m by n, then A transpose is n by m, right? Which means that the number of columns in A transpose is now m, right? Okay, so using the formula from theorem 3.13, right? Part 1 of your formula from theorem 3.13, right? Okay, gives me this so far, right? Right, so that's what I'm using over here, right? And what I want to get is the dimension of the left null space, right? In other words, I want to get this dimension over here, right? So I solve for it, right? I bring dimension of column space of A transpose on the right hand side. And now I start considering this over here, right? Okay, so remember we did an identification of column space of A with row space of A transpose, right? Okay, and similarly, right, well, if you look at this over here, right, column space of A is identified with row space of A transpose, right? Now, if I insert transpose into this, right, column space of A transpose, right, then column space of A transpose you can identify with row space of A transpose transpose, right? So everywhere over here, I'm replacing A by A transpose, right? Okay, so what that says is that the column space of A transpose I can identify with row space of A transpose transpose, which is row space of A, right? Okay, so the column space of A you can identify, or column space of A transpose I can identify with row space of A. And if they're identified as vector spaces, it means that they have the same dimension, right? So this over here, this really shouldn't be equality over here. This is an identification, right? Because on one side over here you'd have column vectors, and on this side over here you'd have row vectors, right? But they isomorphic, right? They essentially the same thing. Once you convert the row vectors over here, once you convert the column vectors here, you'd get row vectors, and then you'd actually have true equality, right? So this over here, column space of A transpose, you can identify with row space of A, and certainly the dimensions will be the same. So that takes you from this equality, from this line over here to this line over here, right? And you just need to remember now that the dimension of the row space of A is in fact by definition rank of A, right? Okay, so that gives me this statement here that the dimension of left null space of A is m minus rank of A. Right. Okay, so this summarizes what we've done in this section, right? If I have an m by n matrix, I have what's called the four fundamental subspaces of my matrix A, right? One is row space, one is column space, one is null space, and one is left null space, right? Okay, so row space of A, and then next thing too is I'm denoting rank of A by small r, right? And this is a notation that we will see later on, right? That you denote the rank of a matrix by the small r here, right? Okay, so I have a matrix A. The rank of A, which is dimension of row space, is denoted by small r over here, right? Okay, so row space has dimension r, right? And that really is just by definition of row space. We saw initially that if I have row space of a matrix A, then dimension of row space of A is called rank of A, right? Okay, so this first, that the row space of A has dimension R, that is just by definition, right? Second one over here is that the column space of A, right, has dimension R, right? And that comes from this theorem here, right? That dimension of row space of A is equal to dimension of column space of A, right? Okay, so if dimension of row space of A is R, right, and dimension of column space is equal to dimension of row space, then obviously dimension of column space is equal to the small r, right? Okay, so this here we saw an example of this. I didn't prove this, right? But we saw an example of where for a specific matrix we saw that the dimension of the column space is equal to the dimension of row space, right? Right, and then now I have that the null space of A is n minus r, right? So n is the number of columns of my matrix, and r is the rank, right? And we saw that in this theorem for null space, right? So in this theorem 3.12, where we talked about null space, right? We stated that when you work out your null space, right, the dimension of it is always n minus rank of A. So that's just n minus r over here, right? And then finally, left null space has dimension m minus r, and that is what we just did over here in Lemma 3.18.